Okay, so let's now continue with the organs of the endocrine system. So the first one we're going to do is the hypothalamus, and I'm going to begin with the posterior hypothalamus. Actually, the hypothalamus is now should be considered as the master gland. In the past, the pituitary was considered as the master gland because it produces a lot of hormones and it affects a lot of tissues. But the pituitary in turn is actually controlled by the hypothalamus, and you'll see the anterior hypothalamus. So the hypothalamus really is the master gland. So it's divided into two parts. It's a part of the brain, so therefore it has neurons in it, and it is these neurons which produce the hormone. So let's look at the posterior hypothalamus first. So there are two areas which are important. They are called nuclei. If you remember from ANP1, a nucleus is where cell bodies of neurons lie. So these two nuclei are known as the paraventricular and the supraoptic nuclei. So this is present in the posterior hypothalamus, and they produce two hormones known as oxytocin and antidiuretic hormone. Another name for antidiuretic hormone is vasopressin. And so you might want to think about what vasopressin would mean. What do you think vasopressin means? Very good, constricts, because pressor is to, put tension or press something, and vaso is blood vessel. So it's a vasoconstrictive, one of its actions is vasoconstriction. And ADH, as the name suggests, antidiuretic. Diuresis means to pass urine. So it's something that makes you pass less urine. Okay? So here, this is produced in the posterior hypothalamus. Then it's produced by these neurons. It travels down their axons, and these axons connect to the posterior pituitary. So if you remember again from ANP1, when axons are grouped together, you have lots of axons together, you call such a structure a tract. So like nucleus was a collection of nerve cell bodies, tract is a collection of axons. So because it connects the hypothalamus to the posterior pituitary, these axons are collectively called the hypothalamic hypophyseal tract, because another name for the pituitary is the hypophysis cerebri. Okay? So hypothalamic hypophyseal tract. So these oxytocin and ADH produced here in the hypothalamus travel in this tract. They come into the posterior pituitary where they are stored. So they are just stored over here. And then when the body needs it, there is stimulation, and from this posterior pituitary, oxytocin and ADH are then released into the bloodstream, because that's where hormones are finally released, right? So this is what the posterior hypothalamus does. Let's look at the anterior hypothalamus. The anterior hypothalamus is connected to the anterior pituitary, which is also known as the anterior lobe of the pituitary, just as the posterior pituitary is called the posterior lobe. And other names are anterior lobe of the pituitary is also known as adenohypophysis, and the posterior lobe is also called neurohypophysis. The posterior lobe is also called neurohypophysis. So let's see what the anterior hypothalamus produces and how it connects to the anterior pituitary. So if you look here, the anterior hypothalamus has numerous neurons, and these synthesize releasing hormones or inhibiting hormones. So collectively, they synthesize releasing or inhibiting hormones. So the releasing hormones are growth hormone, releasing thyroid, corticotropic releasing hormone, and gonadotropin hormone. Those are the releasing hormones. The inhibiting hormones are growth hormone inhibiting hormone and prolactin inhibiting hormone. So when stimulated, the neurons here in the hypothalamus, they release either the releasing or the inhibiting hormones. So they are passed down a tract which ends quite high up. This area which connects the hypothalamus to the pituitary, this part here, this area like a stalk, is known as the infundibulum. It's called the infundibulum. So it's the stalk which connects the hypothalamus to the pituitary gland. So you can see these neurons are coming in this, the neurons have these axons. So the releasing and inhibiting hormones will travel in the axons, but they'll stop short right here. Unlike, remember in the previous slide, the axons went all the way up to the posterior pituitary. So they stop here and they actually release their hormones into capillaries which are present here. These capillaries here in the infundibulum, they come down into the anterior pituitary and again break up into another set of capillaries. So you have two sets of capillaries here. So because this is a set of blood vessels and two capillary plexuses which connect the hypothalamus to the pituitary, this is known as the hypophyseal portal system. It's often called the hypothalamic hypophyseal portal system. Okay? The word portal system means you did in the when you did circulation, remember you had the hepatic portal system where there are two sets of capillaries. So you can see there are two sets of capillaries, okay? So these releasing or inhibiting hormones are released into the circulation here from where they come into the anterior pituitary. And then in response to them, the anterior pituitary will secrete its various hormones. So the growth hormone, releasing hormone, for example, will cause secretion of growth hormone. The inhibiting hormone will prevent secretion of growth hormone. The thyroid releasing hormone will cause secretion of thyroid stimulating hormone. The corticotropic releasing hormone will cause release of adrenocorticotropic hormone. Remember, tropic meant causing release of another hormone. The gonadotropic releasing hormone will cause release of FSH and LH. And the prolactin inhibiting hormone will prevent release of prolactin. When its levels are low, then prolactin is secreted. Okay? So these then again pour their secretions, these cells in the anterior pituitary, they pour their secretions into the general circulation, and these then will go and act on the target organs. Okay? So let's look at this. How are hormones produced in the posterior hypothalamus? How do they reach the posterior pituitary? Very good. Through a nerve tract. And how is the anterior hypothalamus connected to the anterior pituitary? By means of blood vessels, the hypothalamic hypophyseal portal system. So now let's look at the actions of those hormones. So first we'll start with what was produced by the posterior hypothalamus, but comes and sits in the posterior pituitary where it's only stored. So the posterior pituitary does not produce any hormones of its own. It only stores this. So the two hormones which are stored there are ADH and oxytocin. So let's look at what are the actions of ADH, and its other name, as I said, was vasopressin. By its very name, antidiuretic, that means it's going to cause less urine to be passed out of the body. It will do this by causing reabsorption of water in the kidney tubules. So it causes reabsorption of water in the kidney tubules. It will also, you can understand, it will also decrease sweating, anything to prevent water loss. It will also decrease sweating. It also has a vasoconstrictive action on the blood vessels. That's why we call it vasopressin. And by having this vasoconstrictive action on blood vessels, what it will do it will raise your blood pressure, isn't it? Because remember, peripheral resistance increases when vessels constrict. So it raises your blood pressure. So what is the stimulus for its release? Anything which removes fluid from the body, right? Anything which is going to remove fluid from the body, then the body realizes, oh, I've got less fluid, so I need to now conserve whatever. So I need to produce less urine, okay? So anything which removes fluid from the body, which in turn will cause low blood volume and hence low blood pressure. So that's what is going to cause its release. So you can see, when you remove fluids from the body, what happens? The blood becomes hypertonic, isn't it? The solutes increase because you've removed fluid. So the solutes have increased, and we say that the blood becomes hyperosmolar, or the osmolarity of the blood has increased because solutes are more, water is less. Again, if you remove fluid, your blood volume will decrease. Your blood pressure will also automatically decrease. And that's how you can see its action would be to raise blood pressure. And when it causes reabsorption of water, it will try to raise the blood volume back. And pain also causes ADH release. Pain, sometimes very, very severe pain, also causes the release of ADH. Things which prevent ADH release would be if there is too much water. Alcohol. Alcohol is one thing which, not only because of volume, usually when you drink alcohol, let's say you drink a few beers or you drink anything with soda or water, there's volume you're drinking, right? But alcohol, even shots, by itself, it depresses ADH release. So which is why you might have noticed that whenever you have alcohol, you tend to you pass urine more often, and you can get dehydrated if you don't sort of keep drinking water alongside, okay? So alcohol has the opposite effect. It depresses ADH release. How about oxytocin? Its action is on the uterine musculature, so it causes contraction of the uterine musculature. This contraction occurs during labors, definitely. So in fact, it's a positive feedback mechanism. In the case of oxytocin, it's a positive feedback mechanism. But it also, this contraction of the uterus also occurs during normal sexual activity. So it does not necessarily have to do with labor. Because oxytocin, if you do a search on oxytocin, you will find, instead of talking about uterus, most often it will talk about, it is called the love hormone or the cuddle hormone. So that's another name given for it, because oxytocin it's called the cuddle hormone. Oxytocin has been sort of linked to feelings of, generation of feelings of affection. So whenever you feel very affectionate and intimate, then a lot of oxytocin is released. Okay, so that's why it's called the love hormone or the cuddle hormone. It also causes contraction of the myoepithelial cells of the breast. So during lactation, oxytocin causes these tiny cells which surround the glandular tissue, and they cause secretion. So it causes ejection of milk. And this again is very good after labor, because when a child nurses, then oxytocin is secreted and, milk is produced, and then the child nurses even more. And this also helps the uterus to go back to its normal position. So that's another very useful feature of oxytocin. And as I said, causes contraction of the uterus not only during labor, but even during other sexual activity, and even the vas deferens in the males, the musculature of the vas deferens. So that's what oxytocin does. So here you can see a positive feedback mechanism in oxytocin release. So this is, most of endocrine system uses a negative feedback, but here in the case of oxytocin, this is a positive feedback. And what happens is that the head of the fetus during labor, it pushes against the cervix. Nerve impulses from here go to the brain. It stimulates the posterior pituitary to release the stored oxytocin, carried to the bloodstream. It stimulates uterine contraction, pushes the fetus down, which further causes the release. So the loop keeps going around. Okay, the same happens during lactation also. And for ADH, you can see the review up here. So let's look at a case where there is low or what causes its release. There's high blood osmotic pressure. That means there is less fluid, more solute, so the osmolarity increases. In the hypothalamus, there are these osmoreceptors. So they sense that. They cause the hypothalamic cells to sort of begin production of ADH, which travels and gets stored here in the posterior pituitary and then liberated from there, where it acts on the kidneys, causing reabsorption of water from the tubules. The sweat glands also decrease, sweating is decreased. Your blood vessels constrict, so blood pressure is, brought back to normal. It's raised and brought back to normal. So you can see that how ADH is acting. However, if your blood volume is adequate, your osmotic pressure is low, then ADH will not be secreted and all of these actions will not occur and you'll pass more urine. So let's look at some other actions and see some situations when ADH is released or not. So it's antidiuretic. So what is its other action? Yes, very good. Vasoconstriction. So think of all of these scenarios. Which of the following situations would you not expect ADH to be secreted? Excellent, yes, because alcohol by itself, and even if she was just drinking a lot of lemonade, just fluid, so it won't be secreted then. And here, who is likely to produce more ADH? Very good, yes. Elise is severely dehydrated, so she needs ADH. She doesn't want more fluid to get out of her body. These two have enough fluids. And here, that's why I said she has a minor cut. So she's not really bled too much. Her blood volume hasn't been lost much. So, she wouldn't be really producing ADH. Now here, let's look at the anterior pituitary. And as I said, that most of the hormones of the anterior pituitary are controlled by the releasing hormone. So we had growth hormone, releasing hormone. So we had growth hormone, releasing hormone. We had gonadotropic, releasing hormone. We had corticotropic, releasing hormone. And here for TSH, we had thyroid, releasing hormone. So these were the releasing hormones. And growth hormone also has growth hormone inhibiting hormone, and prolactin has prolactin inhibiting hormone. So these come from the anterior hypothalamus, travel to the anterior pituitary. These releasing hormones will cause release of these various hormones. The inhibiting hormones will prevent release of growth hormone or prolactin releasing hormone. And let's see what all of these do. So they go and regulate the activity of other endocrine glands. Remember that humoral way of secretion? Not humoral, the hormonal way of secretion where you had the cycle. So this is called adrenocorticotropic hormone. That means it goes to the adrenal cortex, adrenocortico. So it goes to the adrenal cortex and it causes secretion of hormones from the adrenal cortex. So it acts on the adrenal cortex. TSH is called thyroid stimulating hormone. So it will stimulate the thyroid gland. FSH and LH are known as gonadotropic hormones. That's why we have the gonadotropic releasing hormone. So they will go to the gonads, which means the testes and ovaries, and act on them. So from the testes they will cause testosterone testosterone release, and from the ovaries they will cause estrogen and progesterone release, and you'll see this when we do the reproductive system. Prolactin acts on the breast tissue, causes milk production. And melanocyte stimulating hormone is really a neurotransmitter in the brain. And we won't do too much on that. Growth hormone is one of those hormones which was produced. It has a lot of major functions. This is one of the most plentiful hormones which is produced in the body. And some of the triggers for growth hormone to be released are either the blood glucose is low, or growth hormone releasing hormone is being secreted by the hypothalamus. Exercise, and if you think of it, especially in young children, when they exercise a lot, it helps to spurt growth, so it causes growth hormone release. Growth hormone is actually a lot more is produced during sleep, which is why they say babies need to sleep more. They need to be sleeping for really long hours because it helps production of growth hormone. It is an anabolic hormone. That means it helps to build tissues. So it doesn't break down, but builds tissue. So it's also called a tissue building hormone, which acts on the musculoskeletal system. It causes the epiphyseal plate to causes growth at the epiphyseal plate. So growth in height occurs. But if, say, like you have excess growth hormone which is produced after the epiphyseal plate has fused, then what happens, you cannot grow in height because the epiphyseal plate has fused, then the bones grow in thickness. So they become really thick, and we'll see some diseases like that where the bones get really thick, okay? So otherwise in children it helps to increase their height, helps with the muscular, even the muscular system to develop, acts on all cells and tissues, so it promotes protein synthesis, so helps with cell growth and tissue repair. It doesn't use glucose to produce ATP. What it does is, it does everything to conserve glucose. Instead, it mobilizes fats. It breaks down fats, which is known as lipolysis. And from this breakdown of fats, ATP is produced. So, and in fact, even from breakdown of fats, sometimes glucose is produced. So that's why often it is said it has what is called a diabetogenic effect. That means it raises the blood glucose levels. Because it conserves glucose, so it causes glucose to be stored as glycogen, breaks down fats to use as ATP, and some of the fats which is broken down, glucose is made out of that. So can you see it's raising blood glucose levels, which is why low blood glucose causes its release. Can you see the opposite? When the blood glucose is low, it causes its release. And and because it breaks down fat to make ATP, during the growing period, you would see that children are usually quite lean, especially if they exercise a lot, because more growth hormone is produced. Because fat is broken down, so the children tend to be lean at that time, breakdown of fat. So there's not much collection of subcutaneous fat. Other pituitary hormones, prolactin is a hormone. As I said, it acts on breast tissue, so increases milk production. And even during the menstrual cycle, in the initial part of the menstrual cycle, prolactin is still secreted, which might be the reason why there is some breast tenderness. But because not enough is secreted, that's why it doesn't go on to forming any milk. MSH already told you about. Endorphins and enkephalins are hormones which are produced especially during pain and other times, and these kind of help you to feel good. So they're like the feel-good hormones. So this is a review of growth hormone. So you can look at it. So growth hormone releasing hormone is produced. So it has direct action. It causes fat metabolism, carbohydrate increased fat breakdown, increases blood glucose level. So it acts, unlike insulin, it's anti-insulin. That's why we call it diabetogenic. And the other growth promoting actions, it acts on the liver and other tissues. From the liver, it produces these insulin-like growth factors. So increased skeletal tissue formation, so that growth in height. Then it increases protein synthesis, cell growth, and proliferation. So even the musculoskeletal, all other tissues of the body kind of act on it. And this is how the feedback inhibition is done, and then all of this action will not take place. Okay, so make sure that you kind of look at these review slides of these various hormones. So let's look at some clinical conditions where there is hypersecretion of growth hormone. So there are two types. One is after the epiphyseal plates have fused. So after the epiphysis has fused, now there can be no growth in length, but bone can be keep getting deposited on the outside, right? So that kind of bone deposition on the outside is known as appositional growth. And because growth hormone causes protein synthesis, you will find that a lot more protein is produced, like, keratin, a lot more is produced, so skin tends to get very thick. So the condition which you see is a condition known as acromegaly. So this shows a person, she was a young girl, and she had a pituitary tumor, and obviously she had, achieved her full growth. And this is her stages after a few years. Can you see the shape of her face has changed, because the mandible tends to get very large and, tends to protrude. Skin becomes very thick, so it looks coarse, because again, protein synthesis. Fingers and hands look very, very large, because again, the phalanges and the metacarpals bone is deposited on the outside, so they become very thick. So notice from this stage, this is how she has become, and over a period of time. So her fingers get very large, and each finger is very, very thick. Okay, so this condition is known as acromegaly. On the other hand, gigantism is a condition before the epiphysis has fused. So there is stimulation at the epiphyseal cartilage. Bone keeps, cartilage keeps making more cartilage, and bone keeps replacing that. So the growth in length increases. So these people get really, really tall, as shown in this person. He's reaching the top of the doorway. Can you see this one? So this is known as gigantism. So let's watch a little video on this person who has gigantism.
Winter is rough, especially inside. Luckily, the Kmart semi-annual home sale is on now, and Shop Your Way members get points for every $30 they spend home. Kmart, get in, get home.
In the modern world, only 10 people have ever officially reached a height of 8 feet. In September 2009, Sultan Kozan from Turkey became the 11th. He is 8'1" and currently the world's tallest man, 1 in billion.
In the world, it was a huge boost of confidence for him.
This title became the attention, but Sultan desires more than just fame. He has been a single man his entire life, and now there's only one: true love. Sultan will take him across the world, and for the first time, he will meet someone who understands his condition firsthand. A man almost as tall as he, but Sultan's 8-foot body continues to grow, threatening
to take its toll on his body, the world effect on the heart.
This is the story of the world's tallest man and his fight for survival as he searches for love.
So, growing in height is bad enough, but then have effect on all of the other organs as well. Now here is a condition where there is hyposecretion of growth hormone. So in the case of hyposecretion of the growth hormone, the person is proportional but very, very small. So this is known as pituitary dwarfism. So this pituitary dwarfism is hyposecretion of growth hormone. So you can see this girl, this is all girls of the same age, about 15 years old, and you can see she's only about 2 feet tall. So you can see compared to all of them how tiny she is, okay? And then we have a condition where there is hyposecretion of ADH. So this is another hormone. And this condition is known as diabetes insipidus. It's called insipidus because the urine is insipid. It's not sweet, like diabetes mellitus. When you talk about diabetes, you're usually referring to diabetes mellitus, where the urine is sweet because the sugar is passed out in the urine. So the urine contains sugar. So in these people, because there's hyposecretion of ADH, what happens is they keep passing a lot of urine. So the urine amount is lots. So increased urine, which is known as polyuria. Whenever there's increase in urine formation, that's called polyuria. Because they pass so much urine, these people feel very thirsty. So they have thirst, which is known as polydipsia. But they don't have glucose in their urine. So that's the difference between this one and diabetes mellitus, okay? So here, why are children normally leaned? Let's look at these questions. Lean during the growing period. Yes, very good. Breakdown of fat. And what complication do you think a person with diabetes insipidus is likely to have? Dehydration. Yes, they are going to have dehydration. See, the sugar is not, when I said the sugar is not passed in the urine, the sugar is normal like the rest of us, you know. But because they pass so much urine, they can, and they have no control over it, so they tend to get dehydrated. And you have to actually give them ADH, you have to give them synthetic ADH in order to prevent them from getting dehydrated. So as I said earlier, that we have feedback control. So all of the endocrine organs, or most of them, are under what is called the negative feedback control, where we have, and one good example is here, if you look at this, thyroid releasing hormone from the hypothalamus causes secretion of thyroid stimulating hormone from the pituitary, which goes and acts on the thyroid gland, which produces the hormones thyroxine and T3. When the levels of thyroxine and T3 become adequate in the blood, this goes and negatively acts on the pituitary and on the hypothalamus, so that no more of TRH, no more of TSH is produced. Otherwise, hormone levels would keep on increasing and you would end up with a state of hypersecretion. Then when hormone levels fall, that negative effect goes off and the cycle starts again. So that's why our hormone levels fluctuate throughout the day. So this was a negative feedback response. This was one example. So let's look at this in the pituitary.
Within the base of the forebrain is the hypothalamus, a region of the brain that integrates information from the rest of the body and regulates most of the body's endocrine systems. An example of an endocrine system regulated by the hypothalamus is the hypothalamo-pituitary axis. Some neurons in the hypothalamus produce and secrete thyrotropin-releasing hormone, TRH. TRH is secreted into the hypothalamo-hypophyseal portal vessels and carried into the anterior lobe of the pituitary gland, where it stimulates cells that make thyroid-stimulating hormone, TSH. TRH stimulates the release of TSH from the anterior lobe of the pituitary. TSH enters the bloodstream and is carried to the thyroid gland. At the thyroid gland, TSH stimulates the production and release of thyroxine, a hormone that regulates the metabolic rate of all the cells in the body. In addition to regulating our metabolic rate, thyroxine inhibits Rh-containing neurons within the hypothalamus, resulting in decreased release of TRH, and thus a decrease in secretion of TSH and thyroxine. This is called a negative feedback loop and occurs frequently in the endocrine.
This was an example of you could substitute this for CRH, corticotropic releasing hormone, ACTH, adrenocorticotropic hormone. It goes on the adrenal cortex and secretes what are called glucocorticoids, cortisol and so on, and they have a negative feedback. And let's look at an example of positive feedback.
Attention, recent car accident victims in Tampa. Most car accident victims worry more about the damage to their car than they do their own.
The cell. Enzymes involve chenosis. Which the secretion of a hormone causes effects in target cells that inhibit further secretion of that hormone. Negative feedback is an important way of maintaining homeostasis, that is, keeping conditions within the body relatively constant over time. For example, it is important the level of blood 100 milliliters per 100 milliliters. After a normal fast food meal with a large Coke, your blood glucose levels undoubtedly shoot up well beyond the normal level. Receptors on specific cells in your pancreas detect the increased blood glucose level, and as a result, these cells secrete hormone insulin into your bloodstream. The insulin molecules, in turn, bind to target cells of the body, they're into glucose. This results in glucose levels in your blood going back down to normal levels. Detecting this, pancreatic cells that secrete insulin stop the release of insulin into the bloodstream to ensure that glucose doesn't drop.
So this was another example of negative feedback. You can see that. So now it'll talk about positive too.
Occasionally, positive feedback controls hormone release. Contractions of the uterus early in childbirth causes the release of oxytocin by the pituitary. Oxytocin stimulates longer contractions of the in turn causing more oxytocin release, and so on, creating a positive feedback cycle that continues until the infant is finally pushed out into the world.
So positive mechanisms, and they usually are once in occurring activities. Negative feedback usually occurs in situations where something happens every day. So you can see it gave an example of blood glucose being levels are high, insulin is produced. When glucose levels fall, insulin secretion decreases. So, your blood glucose level rises and falls every day. That's why insulin is produced or inhibited accordingly. Whereas not every day do you go into labor, and not every day are you lactating. So that's why positive feedback mechanisms occur only once in a while, not throughout your everyday cycle. So that's why we see very few examples of positive and more of the negative feedback. Okay, let's look at this. The more a woman nurses a baby, the more prolactin she secretes and the more milk she produces. What is this an example of? Positive feedback. Okay. Let's now move on to the thyroid gland. Very, very vascular gland present in front of the trachea in the neck. It has two lobes. So you can see these are the two lobes of the thyroid gland. These two lobes are joined by a bridge of thyroid tissue, which is known as the isthmus. The word isthmus means bridge. Any endocrine gland is going to be very vascular. So this gland, as you can see, is supplied by numerous blood vessels. And it's present on the trachea, even though it's called the thyroid gland, it's present on the trachea, not really on the thyroid cartilage, as you can see over here. Its lobes, these lobes may go up to the thyroid lamina. So it might kind of extend up to the thyroid lamina. Okay. So whenever you do a tracheostomy where you make a hole in the trachea, you might have to sort of snip this isthmus. You have to be very careful because it's so vascular, so you've got to prevent too much blood loss. Let's look at the hormones which are produced by the thyroid gland. So there are two sets of hormones. One, when we say thyroid hormones, then we talk of these hormones, what are called T4 and T3. But the gland also produces another hormone which is known as calcitonin. So that is not included in thyroid hormone. So we have to separately use the word, okay, the hormone produced by the thyroid gland, calcitonin. But otherwise, whenever you say thyroid hormones, you're really talking about thyroxine, which is T4. T4 stands for T4 is tetraiodothyronine. And T3 is known as triiodothyronine. That means there are 3 iodine molecules bound here and there are 4 in this tetraiodothyronine. Okay? So thyroxine and T4 and T3 are the thyroid hormones. So these are the ones which are under control of that negative feedback mechanism, that TRH, TSH, remember T3 and T4? So this is what is under that control. These are produced by the follicular cells of the thyroid gland, and we'll see a picture soon. So if you look at a histological picture of the thyroid gland, it has these round structures which are known as follicles. These follicles are lined by cells which are known as follicular cells. And it is these follicular cells which produce T3 and T4. And as we'll see, actually what happens is that and these are blood vessels up here. So this is a blood vessel. So iodine is present in the blood vessel. This iodine is kind of trapped by these follicular cells and then taken into the lumen of the follicle. Meanwhile, this follicle produces, apart from trapping iodine, it also produces a kind of a protein gelatinous compound which is thrown into the lumen. There, this iodine and that compound which is known as colloid, that mixes up, or also called thyroglobulin, that mixes up, and then the two are, that mixture is kind of brought back into the cell where it's broken off, and then you get T3 and T4. So I'll show you this picture, but I'm just kind of giving you an example. So it's kind of a little roundabout way, because the cell cannot take in iodine and bind it here inside the cell itself. It has to come into this lumen and bind it, which is why this T3 and T4 are found in the lumen. So that's what I mean by it's seen in the lumen of the follicles, okay? Here, next to the follicles, you have cells which are on the side of the follicles, or they may be present right next to the basement membrane here. These cells are known as parafollicular cells. The word para meaning by the side of. These parafollicular cells produce this other hormone which is called calcitonin. So calcitonin does not go into the lumen of the follicles. Instead, it is secreted directly into a blood vessel. So it comes directly out and goes into the blood vessel. Now in the lumen, more of T4 is actually formed. But when they go to the tissues, that T4 is actually converted into T3, because T3 is the more active thyroid hormone. Compared to T4, T3 is the more active thyroid hormone. Even though more of T4 is formed, that T4 is actually broken down into T3 and it's the more active hormone. So let's look at the actions of these thyroid hormones. And when I say thyroid hormones, again, I'm referring to thyroxine or T4 and T3. They say that if it wasn't for thyroid hormones, we would be couch potatoes. So if you don't have the thyroid hormones, we would just be sitting in a place and be couch potatoes. So, we'd be very extremely lethargic, fatigued, wouldn't be able to do anything. And that's because your metabolism is affected. So what thyroid hormones do is they keep your metabolism active, and they actually raise your basal metabolic rate. So your BMR or basal metabolic rate is raised. So they keep you active. Whenever your body metabolizes, it produces, do you remember we did CO2, which we saw last time in the respiratory system, CO2 and water. But heat is also generated. I mean, think about it. Whenever you do exercise, you start feeling hot, right? So your body temperature also goes up. And because your body temperature goes up, this is known as the calorigenic action. So temperature goes up. And this is called the calorigenic action. These hormones act on practically all tissues of the body, especially during the early growth period. So they regulate tissue growth and development of nearly all body systems. So for example, your skeletal system, your nervous system, your muscular system, everything. So whenever there is less of the hormone produced, especially during the growth period, you will see the problems which arise because these areas were not properly stimulated and they did not develop properly. Okay, so it affects all the systems. It also causes breakdown of glucose. So causes glucose to be broken down, which is called glucose catabolism. Mobilizes fats and causes protein synthesis. So it affects all three: carbohydrates, fats and proteins. As I said, since it acts on all body tissues, it maintains the cardiovascular system function. It maintains blood pressure because what it does is it makes the blood vessels more sensitive. It makes the blood vessels sensitive to epinephrine and norepinephrine. So you can understand with someone has a hyper secretion of thyroid hormones, what do you think their blood pressure will be? High or low? High, because if it's making the blood vessels sensitive to epinephrine and norepinephrine, if there's more thyroid hormones, it will make them more sensitive, right? Someone with low thyroid hormones will have low blood pressure. The blood pressure will be lower than normal, okay? So these are some of the functions of the thyroid hormones. And let's see, this is what I was trying to draw for you. So let's see how thyroid hormone is actually synthesized. So here it shows you a follicle. So here's one follicle. These are the follicular cells. Here's a blood vessel which is lying close by. So here in this picture, they've just taken one follicular cell and the blood vessel close by. So this is one of the follicular cells and a blood vessel close by. And like any normal cell, it has all the cell organelles. It has Golgi apparatus and the rough endoplasmic reticulum. So the first thing is that inside this rough endoplasmic reticulum, this substance called thyroglobulin, which is a protein, is synthesized. This thyroglobulin passes from here into the Golgi apparatus, and then by exocytosis it goes into the lumen of the follicle. So this is thyroglobulin, and it has amino acids called tyrosine inside it, inside the thyroglobulin. When all of this thyroglobulin is present in the lumen, it's very sort of thick and homogeneous, and then it's known as colloid. So another name for it is colloid. Meanwhile, in the blood is iodine which you have taken, which you have, in iodized salt and so on, and that iodide is is trapped by these cells actively, and that then gets converted into iodine. It's oxidized and then also pushed. So it's trapped from here and then pushed into the lumen, where this thyroglobulin is present, and the thyroglobulin has an amino acid inside which is called tyrosine. Now this iodine attaches to tyrosine molecules. So when it attaches to two tyrosine molecules, it's known as diiodotyrosine. When one of the iodine attaches to a tyrosine molecule, it's known as monoiodotyrosine. Can you see that? So your monoiodo will have one molecule of iodine, diiodo will have two. That's why it's called diiodo. When a diiodo and a monoiodo join together, what do you think you'll get? T3, which is triiodo. When two diiodos join together, you get T4. See that? Okay. So T3 and T4, they are formed. They are then taken back into the cell. So now by endocytosis, they are taken back into the cell where they combine with the lysosome. And there in the lysosome, it kind of cleaves this T3 and T4 from the rest of this colloid, from the rest of the thyroglobulin. And then that is now pushed, T3 and T4 is pushed into the bloodstream, and then it travels to the target organs, where the T4 which is present will lose one iodine molecule and get converted to T3 because that is more active. So can you see it kind of has to occur in this roundabout manner, and the combination is done in the colloid. The parafollicular cells are present either here, and so they secrete directly into the bloodstream. So you might have a parafollicular cell present here, for example. So it will secrete calcitonin, which has nothing to do with basal metabolism. It will go directly into the bloodstream, and it doesn't need iodine or anything, so it won't go into the lumen. Okay? So here is a review of the thyroid hormone. So again, you can see this whole cycle. Low blood levels of T3 or T4, they cause because the blood level of T3 and T4 is low. So obviously you want it to be secreted. So TRH secretion is stimulated, acts on causes secretion of TSH from the pituitary, acts on the follicular cells and causes T3 and T4 to be liberated. When the levels rise, then they have that negative feedback action. And obviously you need iodine to produce T3 and T4. Calcitonin, produced by the parafollicular cells, its main function is to reduce the level of calcium in the blood. So it reduces serum calcium. So what would its stimulus be? Something which is causing it to act. That means something which has to be opposite to what its action is. So whenever blood calcium levels are high, that's when this gland will secrete calcitonin, because now it can cause the calcium levels to fall down, right, to reduce. How does it reduce serum calcium? It actually stimulates calcium uptake by bone. It kind of takes the calcium from the blood and pushes it into bone. So this is known as a bone sparing action. That means it doesn't cause removal of calcium from bone. In fact, it builds bone. So it is, in fact, they have a synthetic calcitonin which is known as miacalcin, which is obtained from salmon. And this miacalcin has been used to treat osteoporosis, where bone becomes extremely brittle and fragile because the density is less of bone. Now, osteoclasts remove bone. So if this is when they remove, osteoclasts remove calcium from bone, and when that calcium is removed, it's actually pushed into the bloodstream. Since these guys lower serum calcium, what they do is they inhibit these osteoclasts from acting. So that's how it helps in osteoporosis. It is said that normally the amount of calcitonin which is produced in humans is very little, and it only comes because our calcium levels are kept kind of pretty, normal. So very rarely do you see too much of this hormone being produced, So that's why it finds its use when, there are cases of osteoporosis. Not everybody can take it, but in some cases we can use this. Let's look at some clinical conditions. So when there is hyposecretion of thyroid hormones, you get a condition known as myxedema, which is seen in adults, and cretinism, which is seen in infants or children. Myxedema, so there's less thyroid hormone, so what will happen? The basal metabolic rate is low. So these people are not metabolizing enough, so they are very tired, extremely lethargic. Protein synthesis is not occurring. Remember, that was one of the functions of thyroid hormone. So you'll find that the hair is extremely straggly, skin also is, tends to kind of bruise easily because keratin in protein, which is formed in skin, is not being formed properly. In fact, they say you can actually recognize this, someone with myxedema over the phone itself, because they talk so slowly. They walk also very, very slowly because the metabolism is not going on properly. So it's very inadequate. Not enough heat is being produced. So they don't have enough energy. And it's called myxedema because you have a kind of a jelly-like fluid, a substance called myxomatous tissue, which is deposited in various areas. One of them is on the tibia, and the other one is even in the carpal tunnel. So sometimes these people might present with carpal tunnel syndrome. In cretinism, this is a picture of someone with cretinism. The child is known as a cretin. Where here these children are short-statured because, again, since musculoskeletal growth doesn't occur, since it causes thyroid hormones are necessary for growth and development. So they are very short-statured. Their nervous system is not well developed because, again, remember I said it acts on all the tissues, especially growth and development, and especially during early life. So these children might be mentally retarded. So that's why, as kind of being politically incorrect, sometimes people, when somebody is acting a little dumb or you think that person's not intelligent, you use the word cretin for them. Because biologically, such children who are cretins, their intelligence is affected because the nervous system doesn't develop properly. Then we have another autoimmune condition which is called Hashimoto's thyroiditis, which is inflammation of the thyroid gland causing hyposecretion. So the symptoms will be very similar. So just given named after the person who is, who discovered it. And then hypersecretion of the thyroid hormones could be either normal, just, maybe there's a little tumor in the gland and that tumor is causing increased production of T3 and T4. Or Graves' disease, which is an autoimmune disease where antibodies are produced and these antibodies resemble TSH. So these antibodies are resembling TSH in Graves' disease. So what does TSH do? It stimulates the thyroid gland, right? So this will cause increased production of T3 and T4. So that negative feedback effect doesn't work because you have something else which resembles TSH, which is going on stimulating the thyroid gland. So these people might even have a swelling on the surface of their neck, the thyroid swelling known as a goiter. They often show, because at this autoimmune disease, you find that the muscles of the eye are swollen, fat is deposited behind the orbit, so the eyeballs begin to pop out. So that condition where the eyeballs kind of protrude is known as exophthalmos. Ophthalmos is to do with eye, X meaning protruding out. So this is seen in hyperthyroidism. And it's a very sad condition because, while you can treat it, you can kind of remove the thyroid and so on, the exophthalmos does not disappear. It kind of still remains outside and can be quite problematic because if it bulges too far, then your vision is gone, peripheral vision. You can only look right in front. This is a condition called goiter. When someone, remember we saw a slide a few minutes back where I said iodine is very important for thyroid hormone production. So in fact, there used to be a goiter belt even in the US, I think it was somewhere in the Midwest or something, where less iodine people were taking less iodine. If you're taking less iodine, what will happen? Less T3 and T4 will be produced. So that negative feedback loop doesn't work, which means that the TSH continuously stimulates the gland trying to make more T3 and T4. When the gland gets stimulated, you can see it can grow very large and cause a goiter like this in such a condition. Which is why now you see that, most of your salt and all is fortified. It's called iodized salt, so that you prevent, you make sure you get enough salt. You have a question?
Now, is that why your blood pressure increases when you have too much salt? Is it because it's creating too much of the
Well, no, when you have too much salt with iodine, it's not that you're going to have too much T3 and T4 being produced because then the negative feedback loop will work. The reason salt increases your blood pressure at this is because it draws water towards it. So it increases your blood volume. When the volume increases, your blood pressure increases. That's why. So let's just do a little review on the thyroid, so which is not going to be found in the lumen of the follicle, thyroid follicle. Calcitonin, yes, very good. Okay, let's see. Chelsea has not taken she's not been taking iodine in her diet. What is this likely to cause? Excellent. Yes, very good. So decreased production. If she's not taking iodine, you can't produce the hormones. So the negative feedback doesn't occur. So therefore TSH is not going to be inhibited. It'll keep being produced, will keep stimulating the gland, and so your thyroid will be enlarged. So all of the above. Very good. Okay, why would a person with hyperthyroidism, such as in Graves' disease, feel warm? The correct answer is yes, their BMR is high. All of these things do happen, but that's not why they feel warm. They feel warm because their metabolism is more. So the basal metabolic rate is increased a lot. So when that is increased a lot, then automatically more heat is produced, which is why they feel warm. They do have high blood pressure. Anyone with Graves' disease will have high blood pressure because more T3, T4, remember I said they cause the blood vessels to be sensitive to epinephrine and norepinephrine. Such people will sweat a lot. When you metabolize more, you normally tend to sweat a lot. Such people are also very thin because the basal metabolism is very high, so these tend to be thin. On the other hand, when you have something like myxedema, those people tend to put on a lot of weight. So when people put on weight suddenly and they're not able to get rid of it, one always tries to check on thyroid function, whether there's a problem, okay? So it's because their BMR is high. Okay. Here, again, a little review. Why would a child have mental retardation and short stature? Yes, both of them. Let's look at parathyroid gland. As the name suggests, para meaning by the side of thyroid gland. So this lies actually on the posterior aspect of the thyroid gland. So this is the posterior aspect of the pharynx and the posterior aspect of the thyroid gland. And here you can see the parathyroid glands. There are 4 in number. So they sit on the posterior aspect. They are antagonists to calcitonin. So they also have something to do with calcium metabolism. So the antagonists to calcitonin. So they have something to do with calcium metabolism. The hormone produced by this gland is called parathormone or parathyroid hormone. So parathormone or parathyroid hormone. So their function is to increase serum calcium. So therefore, the stimulus will be when serum calcium is low. Naturally, because you want to bring about the function of the gland, so its stimulus has to be something opposite to what its function is, only then it will come about, right? So when serum calcium levels are low, parathormone is secreted, whose function is to increase serum calcium. How do they do that? They do the exact opposite of what calcitonin does. So they cause osteoclasts to become very active. Osteoclasts break down bone and release calcium. So when that happens, calcium goes into the bloodstream and your blood calcium levels increase. Next, they cause reabsorption of calcium from the kidney tubules. So when whatever calcium you eat passes through the kidney, and most of it is normally reabsorbed. Some of it might pass out if you eat more than normal. But here, these guys, if it's needed, more is reabsorbed so that your blood calcium levels will go up. It also activates vitamin D in the kidneys, and vitamin D is very important for absorption of calcium from the intestine. So you can see even in the intestine, the absorption of calcium is increased. So always it makes sure that calcium levels will increase in the blood. So from bone, the calcium goes into the blood. Increased reabsorption of calcium from the kidneys, again passed into the bloodstream. Increased absorption of calcium from the intestine, that also goes into the bloodstream, so serum calcium levels rise. Okay. So their action, if you have too much of parathyroid hormone, you'll end up with something like osteoporosis, isn't it? Because you'll keep removing bone. Clinical conditions. Hyperparathyroidism is a condition where too much of it is being formed. So obviously bones become very soft and brittle, so they tend to fracture a lot. because calcium levels are so raised in the blood, that calcium can deposit in the kidneys. You can get kidney stones. These people also tend to have ulcers. So it's often said to be a disease of pain, groans, moans, psychic moans. So psychologically also, they groan because of the ulcers in the gastrointestinal tract, pain because of, fractures occurring easily, bone becoming very soft. Psychic moans, it affects psychologically also, it kind of affects them. So they have all these kind of problems. In hypoparathyroidism, where the serum calcium level is low, so here the serum calcium level is low, this makes the nerves extremely hyperexcitable. So any slight touch also will make the nerves sort of hyperexcitable, and the muscles will go into spasm. So the respiratory problems could occur. So the respiratory muscles can go into spasm, and it can cause what is known as stridor, or the person chokes. So laryngeal muscles are constricted like that, and they keep the glottis closed. So that could happen. The person could have convulsions. And such a condition is known as tetany. This is different from the disease tetanus, for which you receive a vaccine. So in tetany, little sort of stimulus will kind of cause a spasm or something, and very often the people have very typical hands. The hand looks very stiff like that. So let's look at a little case of someone who has tetany.
Okay, this is a positive 12-step sign.
So they're just touching the face. Can you see how it's twitching? So that's because of the hyperexcitement. Can you see that? So I'll turn it off. But you could see how it was hyper touch, and it doesn't even light that can bring about hyperexcitable nerve. This is again a good review for you on hormones and calcium metabolism. So you can see calcitonin and parathyroid. So here if you see there's a high level of calcium in the blood, the parafollicular cells will release calcitonin. This promotes deposition of blood calcium into bone and decreases the blood calcium levels. If the blood calcium levels go real low down, that stimulates parathyroid cells. And these cells in the parathyroid gland, they secrete parathormone or parathyroid hormone, releases calcium from the bone and pushes it into the blood, stimulates the kidney to release activated vitamin D, which causes absorption from the gastrointestinal tract, and even here you can have calcium is absorbed from the kidney tubules. Everything is pushed into the blood and blood calcium levels go up. Okay? Which of these would cause parathormone to be secreted? Decreased serum calcium levels. Remember, its function is to increase serum calcium. So think of a function, and what would it be that will bring about that function? So decreased serum calcium will cause parathormone levels, parathormone to be secreted. Okay, so we'll stop here.